Hi everyone, welcome to lecture 4 of Hardware Software Codesign for AGI, and today's topic is quantization. So what we'll be doing is first of all having a general discussion about the data types, and that will be the first part. Then what we'll do is we'll look into one of the quantization methods, which is k-means quantization, and then we'll finally understand linear quantization, and this linear quantization is what we are directly going to use in our FPGAs. So understand all this very carefully. Alright, so in tomorrow's lecture, in lecture 5, we'll be discussing about pruning, but just to give you a heads up, the difference between pruning and quantization. So in pruning, we're reducing the number of weights in general, like the total number of weights which we have learned to calculate and characterize in lecture 3. Those number of weights we'll reduce. But in quantization, we want to reduce the number of bits for each weight. Alright, so the total storage required is, we had calculated is number of bits per weight and number of weights which we have. So this is what the difference between pruning and quantization is. Right now we're discussing quantization, and so we'll review the numeric data types, learn the basic concept of neural network quantization, and binary and ternary quantization we'll skip for now because it will just go out of the length, right? Later on we can cover it. And okay, in this diagram only let's understand what is continuous signal and what is quantized signal. So quantization just basically means discretizing. It's the same meaning of the word quantum, where the word quantum physics comes from, like a small packet of energy instead of a continuous spectrum. So here the signal which you see, this signal is actually a continuous signal. But if we quantize it, then this signal can basically lie on any value on the y-axis. Like this can lie on any value on the y-axis between the max, hmax and hmin. Right, hmax and hmin. This continuous signal can give any output. So sometimes it becomes very troublesome to store, and it becomes also difficult to differentiate that what is the difference between the two signals. So most of the real world things are actually like what we observe in the classical mechanics are continuous. But then if we tend to discretize it, we tend to quantize it, it can get only certain values, maybe 0, plus 1, plus 2, minus 1, minus 2, as can be seen in this example. Alright. So the motivation for quantization is actually the same as anything, make everything cheaper, which includes your storage, your number of calculations that you have to perform, mathematics and calculations, right? And just try to observe this low bit width operations are cheap. So if you do 8-bit AND versus if you do 16-bit AND, so you see almost 30 times or a 32-bit float AND, right? So you see that if we just go from 32-bit add to an 8-bit add, obviously from float to int, we get a 30x reduction, and it is reducing. Like if we first of all from floating point only we change to floating point 16-bit, it has reduced, and then from 32-bit int, you can see it is further reduced, and 8-bit int and it's almost 0.03 picojoules. So much you're saving actually. Same is the case with multiplication. Obviously in multiplication the reduction is not linear, it is more like quadratic. So because that's the nature of multiplication. When we go, then you will see that how many additions are actually happening inside the multiplication. That pattern is quadratically decreasing. So how should we make deep learning more efficient? Is definitely by choosing a more efficient data type. So let's have a discussion about the different data types which we have available with us, and how is numeric data represented in modern computing systems. So when it comes to integer and we take unsigned integer, then we have an n-bit range, and if we have an n-bit range, then the range which we can go is from lower limit is 0 to the maximum limit of 2 raised to the power n minus 1. Alright, so this is the range which you can get. But there is a huge issue in this, that how do you represent negative numbers? So this is a typical example of how you do an n-bit unsigned integer. So what we do is we say that, okay, let the first bit represent the signed bit. So the n-bit range is minus 2 raised to the power, so from 2 raised to the power n we divide by 2 because we're splitting it into half. So 2 raised to the power n minus 1 and 2 raised to the power n minus 1 for the positive half. But here the issue is that we're actually both all zeros, and the sign bit one followed by zeros is representing a 0. So why to waste a slot, right? So we go to 2's complement representation, and in that what we do is the 1 followed by all zeros represents the lowest possible number, which is minus 2 raised to the power n minus 1. Alright, so that gives us no wastage of slots, and the n-bit range of 2's complement representation is minus 2 raised to the power n minus 1 to 2 raised to the power n minus 1 minus 1. So this is very important to understand. Let's have a discussion about fixed point numbers. So in fixed point numbers, the point which you are choosing to split it, that's fixed. So if there is a number which you are given, let's say 0, 0, 1, 1, 0, 0, 0, 1. So where your point is, from forward to that point, you give 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, and just this bit you can use as minus 2 raised to the power 3, like, you know, it can have the negative weight. For the numbers which are before the point, you do 2 raised to the power minus 1, 2 raised to the power minus 2, 2 raised to the power minus 3, 2 raised to the power minus 4. And that's how you can get this number. Another way to get this get this number is that you take this number as, like, you know, as it is, like an int number, and from here only you do the calculation. But then you scale it, you multiply it by the 2 raised to the power minus 4 coming from where the fixed point is. So this is how the computer calculates this 3.0625. This is much more efficient way of calculating. Now floating point numbers. So there can be multiple representations of a floating point number. So this is where most of the machine learning calculations, modern deep learning, like deep learning models, they actually are all in floating point numbers. Most of the computation which you do, it's also in floating point number. And the reason you will be seeing in just a moment that why 32-bit floating point number versus is preferred over fixed point and integer in terms of its calculation abilities, right? So here the number is split. So we are doing the 32-bit floating point, we are understanding this, and you can extend the same concept which we are learning in 32-bit to any 16-bit, 8-bit, and I'll show you in the example, one example in the end. But point is that you need to learn how to actually extend the same concepts to different floating point numbers. And this is specified in IEEE 754. So what we do here is that the 32-bit number, we split it into 3 parts. 1 bit we take it for the sign, then we choose 8 bits for representing an exponent, and a 23-bit we choose for representing fractions. Now here this exponent is what gives the whole representation, the whole floating point number representation, a very dynamic range, because you cannot just move linearly, you can move exponentially in some direction by changing a single bit here. Alright, so in general, if you're given this number, then how you actually calculate the number, okay, so given any bits filled in this, how you calculate the number, that is through minus 1 raised to the power the sign bit, so the sign bit comes here. Then what you do is, the representation itself, so this is the most standard form, this is known as the normal form of representation. We'll see a few other edge cases, but understand the normal form of it right now. We do 1 plus fraction bit. So this is how the specification is. So whatever 23-bit fraction you have, you add it to 1 and you do a multiplication here. And then 2 raised to the power exponent minus 127. So whatever exponent you are calculating here, that minus 127. So this 127 is known as the exponent bias, and it can simply be calculated by whatever the number of bits you have. Let's say there are 8 bits, so the exponent can be calculated 2 raised to the power 8 minus 1. Okay, and this is to actually give both the positive and the negative exponent, so that's right at the middle point, right? So how to represent this 0.26265625 in terms of floating point number? We'll do both the examples of reverse conversion as well as representing it in that form. So as we told that anything needs to be represented in 1 plus fraction form, right? So the sign bit is definitely positive here. What we'll try to do is effectively break it into 1.06 some number in between 1 to 2 into a scaling factor which is determined by 2 raised to the power minus 2, like what this number is. So you need to actually effectively break it. It's like smart calculation as of now. There is a methodology as well, but for now just a smart calculation. And this 1.0625 can be represented as 1 plus 0.0625 into 2 raised to the power. Now we have to represent as exponent minus 127. So it's minus 2 here. So we'll put 125 minus 127. So now this 125 will actually be represented here, and this 0.625 will be represented in the fraction, and whatever the sign bit is, that will be represented here. So that's how you effectively break a number. For representing 0.0625, it's simple and straightforward, like it's elementary number systems which we do, how to deal that. And here the case is also very simple, that it's just 2 raised to the power minus 4, right? 2 raised to the power minus 1, 2 raised to the power minus 2, 2 raised to the power minus 3, 2 raised to the power minus 4. Every time it gets half. So here it would be 0.5, here it would be 0.25, here it would be 0.125, here it would be 0.0625. And this you're presenting as 125. You can use calculators for doing all this, like in your Casio calculator, there is an effective method of figuring out what is 125 in this, what is 0.0625 in this form. But the main question is how to represent a 0 here, right? How do we represent a 0 here? So for that, what we do is, before we actually get into that, so there are two representations of 0 here. Obviously some slots you will see that many slots here are wasted, but as per the prescription of the IEEE 754, there are two representations of the floating point number. One is the normal representation and another one is subnormal representation. So in normal representation, whenever our exponent is non-zero, it is known as normal representation. Whenever our exponent is equal to 0, it is known as subnormal representation. Because a natural question for you would be that in the normal representation, if I have to represent 0, let me make fraction bit as 0 and let me make exponent as 2 raised to the power like something, so that's just into 1. But there is no factor of 0 coming in here, so we'll have to bring in some factor of 0, right? And that's why we have subnormal representation, in which if this I symbol here is that it is fixed here. So if exponent is 0, that means all these bits are 0, then computer internally knows that I do not have to do 1 plus fraction, I just have to do into fraction. And here the fraction, if it is 0, then also it will lead to the whole representation of 0. And if the sign bit is 1, then also it is going to represent 0. So there are two slots for 0 in this. But let's now ask, what is the minimum positive value which is possible? So pause the video, think about it. What is the minimum positive value which you can think of? So obviously you cannot represent something infinitesimally small, like very small. So it has to be certain, like what is the smallest positive value, and when dividing you have to be sure of its numerical stability, that it doesn't blow up. So let's do it this way, that obviously 1 plus fraction would lead to giving you an unnecessary 1 plus, which you do not want. So the smallest positive subnormal value, smallest positive value has to be in subnormal representation, and in that the smallest number you would get by this this thing is already fixed. It's going to be 1 minus 127, right? This part we consider it fixed. In subnormal, if exponent is 0, then we just assume it to be 1 minus 127. So this 1 minus 127 is 2 raised to the power minus 126. So this is coming from here. And this factor, just a second. This factor, fraction, the smallest possible is 2 raised to the power minus 23 if you just put last one bit here. So the smallest possible number representation is 2 raised to the power minus 149. Now in the same case, what is the largest possible subnormal value? So obviously the answer is right in front of you, but think about it. Like right now it's obvious to you, but when I first attempted this question, I actually just put a 1 here. So I was like, the smallest possible representation is 2 raised to the power minus 126 into 2 raised to the power minus 1. But that's not quite right actually. Like if you have to reach the positive value, then all these are getting added internally, right? So you add 2 minus 2 raised to the power minus 23 and 2 raised to the power minus 22, you add all of them, and that's how. So this is actually a GP series, and this would give you this answer, 1 minus 2 raised to the power minus 23 into 2 raised to the power minus 126. How do you get this factor here? Because the fraction bits which you are adding, so this is 2 raised to the power minus 1, this is 2 raised to the power minus 2, 2 raised to the power minus 3, all the way up to 2 raised to the power minus 23. So this forms a GP. So how do you calculate this in terms of GP? You add 1 plus 1 and minus 1, and then according to the geometric progression, that if your first term is a1 and you have to calculate s of n up to n terms, then it's whatever the first term is into 1 minus the ratio raised to the power the total number of terms which you have. So how many terms are there in this GP? 24 terms, 23 coming from here and 1 which we added. So 1 minus, and every time it's getting divide, r is here what? 0.5. So 1 minus 0.5 raised to the power 24 upon 1 minus 0.5 according to this formula which you see right here. So this would give you 1 minus 2 raised to the power minus 23. Alright, and then you multiply it with 2 raised to the power minus 126 in order to get the largest possible subnormal value. How is the representation of infinity in this? Sometimes if you've already used Python before, so there are two particular numbers which you see, not a number nan coming and infinity. Like both these are like valid representations in FP32. So in normal number representation only, if exponent is not equal to 0 and this whole thing is 0, the fraction bit is 0. So what we saw is that if exponent is 0 and this is 0, then it would mean a 0. But if the exponent is fixed to all ones and we fix the fraction bit to all zeros with the sign bit as 0, then it is plus infinity, and if this is negative, it's minus infinity. And if it's fixing exponent to all ones, actually fixing exponent to all ones is a special case, and no matter what after that, if you have any number inside this, it's not a number. So it just checks that if the exponent is all ones, and then if this is non-zero, then it's just not a number. So it's so much waste actually, so much of waste, so many slots are wasted. So this is a summary of FP32, and we see that after plus minus 0, the smallest possible representation root is from minus 149, and the largest possible subnormal value is 1 minus 2 raised to the power minus 23 into 2 raised to the power minus 126. Then the normal value, the smallest is 2 raised to the power minus 126, and the largest value possible is this, with infinity and plus infinity, minus infinity, of course. This is like a summary table, and what we actually need to understand is that why floating point 32 is important. So here we see that we're expanding the dynamic range. By just changing one bit in the fraction, we can actually go we can expand the dynamic range of our representation, and it's very useful for training neural networks. especially in the first couple of iterations when the neural network is highly turbulent and when the gradients can become quite large. So we want to fit in those large mathematics which you've calculated. We want to fit in those large calculations in our representation of the in our representation. So that's why many times we just, even when deploying, so most of the times quantization and pruning and all these techniques are used when we're deploying it in our machine learning model, not when we are training it. And if you notice it, we have not discussed the training portion much in our machine learning introduction as well. We have mostly focused on deployment, on inferencing part, right? So for doing the training portion, still FP32 is used because it has its own advantage of giving us the dynamic range. So like the IEEE 754 single precision 32-bit float number, we have IEEE 754 half precision 16-bit floating point number. So in this, what we do is, the first bit is obviously the sign bit, and we reduce the exponent bits from 8 to 5, and the remaining bits, which is 10 for the fraction. So 10 plus 5 plus 1 for sign bit gives you total 16. So fewer number of bits to train the neural network, but much smaller dynamic range, as exponents determine the dynamic range. So as you reduce the number of exponent bits, the dynamic range of your representation decreases. So what Google did for is made a new representation called as brain float BF16. So it maintains the high dynamic range. And BF16 is a very popular choice of representation in LLMs because it helps LLM converge faster than using FP16. So you do the same machine learning model, you do the same training. In one you use FP16 and in another one you use BF16. So just by being able to represent a more high dynamic range in the mathematical calculations, you are able to converge faster. And here the exponent bits are 8 and fraction bits are 7, so total bits 16. So it's time for a small quiz. Actually, the answer is right in front of you, but still spend some time and get some practice. So as I told, that the same concepts which we have learned in FP32 extend here as well. So if it's an FP16 number, the equation in the normal range would look the same: minus 1 raised to the power sine upon 1 plus fraction into 2 raised to the power exponent minus bias. Here, how many terms you have for the exponent? 5. So what will be the exponent bias? 5 minus 4, which is 5 minus 1, which is 4. So 2 raised to the power 4 minus 1, which is 15. So 15 is your exponent bias. So anytime you have to actually calculate what this exponent is. So this 1,001 is what? 17. 17 in decimal representation. 17 minus 15 gives you 2. And fraction part, if you look at, then fraction part is simply 0.75. You just add these two bits. So the decimal answer, what this number represents in decimal, is nothing but negative 1 plus 0.75 into 2 raised to the power 2, the exponent which you have calculated. Same, what is the decimal? 2.5 in brain float BF16. So here, since there are 8 bits in exponent, so exponent bias would be same as FP32, which is 127. And the sign is positive. You calculate the exponent in binary, what it looks like, and what is your fraction bit. So it's 0.25, and which is in binary looking like this. So the answer is finally this: 0, 1 followed by all zeros, 0, 1 followed by zeros. So this is representing 2.5. You actually, if you're confused how we're calculating this 1 and 0.25 here, it's because we've effectively broken down it into 1.0.25 into 2 raised to the power 1. So that's how we're getting 1 and this thing here. So NVIDIA further reduces. So like if you can go up to 16 bits, why not go further down to 8 bits? So this further reduces the memory footprint, making training faster and cheaper. And one thing which you definitely need to understand is that during training we want higher dynamic range. Like we want the gradients to converge quickly. We want being able to represent higher numbers in our representation, which is not possible using int 8, right? Int 8, what is the maximum range you can go? 2 raised to the power 7 minus 1, right? So that's not a very big number. So we want to utilize the concept of exponents in order to represent higher numbers, higher values for us to do the calculation and mathematics on. So NVIDIA came up with this FP8, 8-bit precision, floating point 8, one they called as E4M3 and one they called E5M2. And so if E5M2 is what is used for gradient in the backward, and you can obviously see that, as we have told, for representing higher gradients, you want more number of exponents. So they do this for doing the forward pass, and they use FP8 E5M2 representation for calculating the gradient in the backward. So they make the switch in the output end, like, once they change the representation and how these data types are being used. If you've done embedded systems course and other courses in computer architecture, you will be knowing that how the processor is able to understand the data types. It's in the instruction set architecture itself. So it's just that the nature of instruction set architecture has changed, and that's how you tell the processor it's a different data type, so do the calculations differently. So the quest for fewer numbers of bits doesn't stop. We try to actually go even further to int 4, and then FP4 we have 3 representations of E1M2, E2M1 and E3M0. So let's quickly look at all of them very quickly. So it's important to think from an understanding perspective, not from rote learning perspective, but from an understanding perspective that what is actually happening here. So in int 4 representation you have and if you're considering the first bit to be the sign bit, which you have to, because we want to represent the negative numbers as well, right? So in one direction you can get 0, 1, 2, 3, 4, 5, 6, 7, and in another direction -1, -2, -3 up to -8. So this is like the 2's complement representation which we are following, so that we don't waste 2 slots here. So this is the 2's complement representation, and in one single direction you can see all these are linearly spaced. The same gapping is there. Okay. Then in FP4 representation, if we give exponent 1 bit and the mantissa part 2 bits, then what we can do is, there are again going to be 2 cases, subnormal case and normal case. So the representation remains the same, if exponent is 0, then we go to the subnormal case, because we want to represent 0. The main thing is that 0 cannot be avoided, so we need to actually have a subnormal case. And in the normal case, we just do 1 plus 0.75, right? So if both of them are 1, 1, then it's 0.75. So we do 1 plus 0.75 into 2 raised to the power 1 minus 0, which is 3.5. This is the largest number which you can represent. So if you map down all the possible combinations, you will see that we can go from 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5. It's also linearly spaced, but actually it's the same thing with a scaling factor. Alright, so this is not giving us much advantage. We're just able to represent certain numbers which we were previously not, which is 0.5, which is like a smaller number we're able to represent right now. We then try to increase the exponents. So if this is 1, 1 and this is 1, then 1 plus 0.5 into 2 raised to the power 3 minus 1. Why minus this exponent bias? How are you calculating here exponent bias? The number of bits minus 1. So here the number of bits was 1, so 1 minus 1 is 0. Here 2 bits are, so 2 minus 1, this is exponent bias is 3 minus 1 here. If you do the map it out onto the number line, then you will see you will have a much more slightly more dynamic range. And they are not even linearly spaced, because you are having 2 exponent bits, so it's not just a single scaling factor which you are having. And then we go to the extreme case of E3M0. In E3M0, the fraction bit is always going to be 0, so no point on calculating the fraction bit. Here also there is no infinity and not a number possible with us, because it's just like, if we do that, the infinity and not a number cannot be represented in this. We don't have sufficient bits to represent that. Here you can see we have a much more dynamic range, and from 0 to 16. So number of points effectively remain the same. The number of things which you can represent with 4 bits, they remain the same. but the dynamic range, the range which we are able to go, that differs with the representation style. So again, with this understanding, you can pause the video, take a break, because we are going to switch gears to what is quantization. Okay, so as we have already discussed about what quantization is, the process of constraining an input from a continuous or otherwise large set of values to a discrete set. And all these numbers which you see on top here, they will be actually mapped down to this number. So each of them will have a quantization error, like what it truly was and what we're representing it to be. So definitely there's a loss of quality, like if original image is there in 16 million colors and we just map it to 16 color images. So we take the most prominent repeating pixels and we try to represent the image with that. And there are multiple algorithms of what those 16 colors, color palette has to be, and then from that we can reconstruct the image. So there are several techniques for quantization, and in the naive approach, we just take 32-bit FP32 to represent our weights and activations. Activations is what we're referring to as the inputs coming in that layer, and weights is what we're multiplying that, like which is getting trained, right? So there are two things, weights and activations, and definitely the storage in this is going to be floating point, and the computations are always going to also going to be in floating point. What we do in k-means quantization is that, just ignore this paragraph as of now, it's just not of like, just ignore this right now. We'll do the storage of in k-means based quantization. What we do is, whatever the weights are, whatever the weights are, we represent them in floating point code book. Like we do the integer weights, and then we have a floating point code book which you see here. In a minute, I'll tell you how we calculate that. And then we have the arithmetic, whenever we have to do the arithmetic or the computation, which is weights into activation. Whenever we try to do that, we convert from this integer representation to a floating point representation. So the computation is always in floating point arithmetic, and this is the case with the modern LLMs. In modern LLMs, there are 175 billion parameters, like 175 billion parameters. Just imagine the scale. And if you choose each 175 billion parameters, and if you choose for each parameter a 32-bit or a 4-byte representation, then you can just imagine that how many gigabits it would be. 170, almost like 14 point, more than 14-15 GB just to represent the model. So we want to effectively reduce that. So we have, it will be approx 15 GB, so that's just too much waste. And what we want, so basically you get the motivation that computation is not a problem, because computation we're doing layer by layer. We're not doing multiplying 175 billion parameters at once. So computation is not an issue. We're just taking a subset of those and then multiplying them. So the floating point arithmetic can very well fit into the memory size. But the representation of the model itself crosses 14-15 GB, which is like, many of our laptops have just 8 GB RAM, so it's not even possible to fit in. So how it works is, simple. Instead of, so whenever you have a weight, so we're considering a weight matrix of 4 cross 4, total 16 weights. In real life, these can go up to like 16 million or something, or what we have seen in, depending on our convolution or the fully connected operations, there can be many weights, right? But we're just taking a small, for example, in here all these values which are close to 1, close to 2, 1.2, 1.87, we represent all of them with 2. That's what we try to do. So you might be figuring okay, as humans we can just map out all which numbers to choose in the code book. That depends on us. But point is that these centroid values are also trained. Like we begin with random things, and then based on how to actually represent this whole thing, we choose mathematics, like to figure out what is the most effective choice here, which would lead to the least quantization error. So what we do is that if we have, let's say, for the code book, we have 4 slots with us. So to represent 4 slots, how many bits do we need? 2 bits we need. So 0, 1, 2, 3. Now, based on the value which is inside the centroid, we try to map the weight matrix into that. So I've color coded it just to help you understand that this 2.09. So if it is belonging to, if it is closest to this centroid, this value would go into the weight matrix. So instead of storing the weights, actually, we're storing the addresses of the values which are available in the code book. So if we reconstruct this from the centroid and the cluster, if we reconstruct the weights, then in place of 3, what will come is 2. In place of 0, what will come is -1. So you will see that effectively it's still, the color coding is still the same, but we calculate the quantization error, and the main aim of finding these centroids, appropriate centroids, is to minimize this quantization error. So let's do a very quick calculation of how much space we are saving in this. So originally 32-bit floating point number was taking 32 bits and total number of weights is 16. So 32 bit into 16 is 512 bits or 64 bytes. This is 64 bytes. Now mouse pointer I think would be better to show in this case. Here 16 weights are there and each one is using 2 bit because there are 4 boxes we have chosen, 4 slots we have chosen in the code book. So for representing each 0, 1, 2, 3, we need 2 bits. So it's 2 bit into 16, which is 32 bits, which is nothing but 4 bytes. But along with this 4 bytes representation, we also need these centroids, and these centroids are still 32-bit numbers because we are choosing floating point representation. So it's still 32-bit numbers. And how many of such numbers are there? 4 numbers. So 32-bit into 4, which is 20 bytes. So we do an addition of 4 byte plus 20 bytes, and it's sorry 32. I'm sorry. This calculation is 32-bit, and 32-bit into 4 is 16, right? So 16 plus 4 gives you total 20 bytes. So how many times smaller? 3.2 times smaller, and this is just for the scale when your number of indexes is the number of weights which you have chosen is just 16. But now assume an n-bit quantization with number of parameters as m. So originally when 32-bit number is there, then the total bits which is taking is 32-bit into number of parameters is 32m. Versus when you have done n-bit quantization, we're just generalizing from 2-bit to some, let's say, n-bit, because in 2-bit quantization you can just have 4 representations. In 4-bit quantization you can have 2 raised to the power 4 representations, and so n into m bits, and for along with that there are how in the code book, as we have discussed, 2 raised to the power n code books will be there, each having 32 bit. So if the value of number of parameters m is very large, then you can simply ignore this constant part because this is not at all dependent on m. This is just dependent on the quantization bit, right? So if we can ignore this part, then you can see that based on the quantization, the number of bits you're choosing, it will be 32 upon n times smaller than that. So if the value of n is, let's say, 8-bit, then it will be 4 times smaller. So directly you can bring down the model size from 16 GB to, let's say, 4 GB. So it's a huge space saving actually when you consider that it has to be replicated at so many servers across the world. So if there are 100 servers, then you are directly saving 400 GB, which is actually huge. Then is the question of how do we fine tune the models, because all these models have to be fine tuned, right? So it's basically weights getting trained. So if you ignore this part right now, if you ignore this part, what actually happens in machine learning models is that this weight is trained. Like instead of 2.0 in the next pass, it would be 2.10, because that is giving much lower loss value. So these weights are actually trained. Activations are coming inside, these weights are trained. So how do we train the weights? We train the weights definitely in quantized world by changing the centroids. So we do the whole operation in the same way, like, we have the weights, we clusterize them using k-means clusterization, and k-means algorithm, and then we calculate the gradients. Whatever the gradients are, we color code them to be in the same, like in the same weight matrix. We color code them to be, because finally the calculation, if you remember, is happening in floating point. So the gradients which you obtain are again in floating point representations. But we actually color code them, and like 0.03, 0.03, whatever the gradients belong to the one single color. So we group them together and we do an average operation to just reduce them into a single number. And this 0.004, we try to actually multiply it with the learning rate and do the gradient operation here. So if it is 0.04, then from the centroid we deduct this 0.04 and we obtain the new fine-tuned centroids, which will give a better machine learning model to you. So how does the model accuracy change with quantization? So you can see that on the x-axis we've plotted the ratio size, the compression ratio. So if it was originally 100 MB, the model was originally 100 MB, then if we compress the model to around 20 MB, we'll see that there is always like no loss till that point of time. Up to like if we reach around 10 MB or so, we're having negligible accuracy loss. We don't want the accuracy to drop, because as the number of bits we are decreasing, our accuracy will surely decrease, and there will come a point of time when you can no more represent the machine learning model properly. So with quantization only you be able to reach till that point. With pruning, since you are cutting down the weights, I'm just presenting it here. With pruning, since you're cutting down the weights, you still are able to reach at around 8-10% with minimum loss of accuracy. But if you do pruning and quantization together, and that's when actual real magic happens, and you can reduce the model to around 4 MB or so. And we'll come to this slide. Okay, let me explain it right now only. So before quantization, we had weights, like so this is representing the count. So if there is this value, whatever it is, so in these 2 points, most number of weights are there. And after quantization, definitely we discretize the weights. Not all possible weight values are possible, so only this and certain weight values are possible. And in that also we see that the count is, majority of this is actually like represented to this point, majority of this is actually represented to this point. You see there's a small dip here, so which represents this dip. So the number of weights which are mapped to this single line is actually reduced. And after retraining, you will see that the centroids, the weights will shift. So it's not evident in this image actually, but the weights have shifted a little bit to the left or to the right based on the gradients which we've calculated and through back propagation. So how many bits do we actually need? So this is like standard question. So accuracy starts to drop, so no point in decreasing further number of bits. So here we are calculating two metrics, top 5 accuracy and top 1 accuracy. So you see that in the quantize, which is represented by triangle. So initially with 8 bits, 7 bits, 6 bits, 5 bits, 4 bits, so all these are representations actually, like we've discussed the standard representations, but because that is much more effective for the processor. But you can actually mimic a soft processor in which you can do 7-bit operations, 6-bit operations. You don't fabricate it in real life, but you can still do the calculations. So these are number of bits per effective weight in all convolution layers, and this is fully connected layers. So you see that in fully connected layers, we can go further to 2 bits, but in convolution we can go up to 4 bits only. If you try to reduce it beyond that, then things are just gonna break. So there are two metrics, top 5 and top 1. So top 5 is when the thing which you have calculated, the output, machine learning output, that lies within the top 5 in the ground truth table. Let me explain it properly. Let's just understand top 1, that if the correct class was, let's say, dog, and what your machine learning model is predicted as dog, then it's correct. If it is represented as cat, then it is wrong. But in top 5, what we do is that if it is, we take the top 5 guesses which the machine learning model has: cat, plane, human, and dog, and then let's say tiger. So we classify this as a correct output. So that's why you see that the accuracy increases if we take the top 5 margin. We're just giving some little bit of relaxation to the machine learning model that whatever output you've given, that can be in the top 5 predictions you have made. So you might be wondering that, okay, we're discussing 8-bit and all this isn't like, thing of like 2005, 2004, why are we discussing it now? Because in AI accelerators, it is still like, Snapdragon 8 Gen 2, which got released, I think, earlier this year, in 2024. They actually have, they actually have a 4-bit representation of ints and floating points. So you can see in this, I think they have mentioned in this slide, yes, supports all precisions, int 4, int 8, int 16, fp16, and supports mixed precision calculations also, int 8 and int 16 together. So this is their hexagon processor which they have inside for doing the smart AI. I would highly recommend that you just go over through their website and see, because this is like industry thing, and we need to be aware of what all things, what we're doing in theory, what is actually like, available in the market. So using the Snapdragon 8 Gen 2 and doing calculations in int 4, like representing your model in int 4, you'll be able to do very fast calculations because it supports int 4 operations. So these are just certain features which I've placed here. You can actually pause the video and just go through over them. Our main thing which you have to understand is this int 4 precision, which is available in Snapdragon processor. And then finally, like just we do the pruning, we do the quantization, and then there is a Huffman coding, in which what we try to do is squeeze, like, the extra little space which we have, we try to save even that. So understand it very simply, that the weights which are in this range, let's say, so since the count of these weights is higher, so we try to actually represent these weights, the frequent weights, using less number of bits to represent, and the infrequent weights we use more bits to represent to calculate, like, to maintain the precision. But whatever the number of weights which are repetitively coming. So simply in Huffman encoding, the goal is to minimize the overall length of the encoded data, and this is done by assigning shorter codes to the more frequent weights which are coming and longer codes to the less frequent weights in the network. So it's simple, and we're not going into the mathematics of it, just to tell you that we try to squeeze it down further. So as a summary of some deep compression, we have the original network with the original size here, and then pruning, which we're going to, discuss later. We reduce from 9 to 9x, almost 10 times reduction by pruning. So lesser number of weights, then we do the quantization, which is less bits per weight, and we get 27x to 30x reduction. And finally we do Huffman encoding, which is, so these two are industry standard, we definitely do them in our FPGAs as well. This is something 35x to 49x reduction you can get by doing Huffman encoding, but at the cost of you have to decode it also. So many times we just avoid it because it leads to extra time as well. But if you're really memory constrained, you can go for Huffman encoding as well. So some deep compression results are like, so Lenet was really old machine learning models, really old deep learning models, and you can compress them to around 40x, 39x original size. This is the compressed size, so you can calculate based on that while maintaining the same accuracy. Like, the accuracy calculations, somewhere you just see it improve, but it's broadly the same. That's what quantization can, deep compression can help you not like just increase the accuracy, but maintain the accuracy, something what we really want. These numbers are just like, maybe some edge cases, some things which this just gotten right. AlexNet, VGGNet, these are the modern deep learning models. So you can see, like, for VGGNet, which was represented as 550 MB, got reduced to around 11.3 MB while maintaining the same accuracy. So almost 50 times reduction. In GoogleNet, almost 10 times. In ResNet, again around 10 times reduction. So point is that can we make compact models to begin with, instead of first trying to compress, like we make a big model and then we try to compress it using this pruning, and can we just actually begin with a small model to begin with? So answer is yes. And just to this topic we'll explore more in neural architecture search, and we try to make a machine learning model smaller in the first place and then apply these techniques. So here we'll look into SqueezeNet later, but I just wanted to tell you at this point of time that yes, we can make smaller things, and SqueezeNet is a competitor of AlexNet. And so you can see that in SqueezeNet, after doing the deep compression, so the top 1 accuracy and top 5 accuracy is on ImageNet dataset here, and it is actually able to maintain the accuracy with 510 times being 510 times smaller. Alright, so it's just 0.47 MB. The original SqueezeNet is 4.8 MB, and then after applying deep compression it is 0.47 MB. So this model in itself, without any deep compression or anything, is already 50 times smaller. So yes, we can begin with a compact model to begin with. And the main thing which we do here, just to give you a high level overview, is we do a convolution, 1x1 convolution, to squeeze 64 channels into 16 channels, and then we do the expansion operation, one using the 1x1 convolution, because the output is in our hand. Whenever we do a convolution operation, this we have learned in lecture 2, lecture 3, that the output is always in our hand. So 64, we can expand it to 64 dimensions, and the output, total output, we can again concatenate this and we can get 128 channels. So this is the basic principle of SqueezeNet. So what is actually happening during k-means based weight quantization is during computation. In storage we do this operation, we represent it like this, but during computation we again convert it back to 32-bit floating point operations based on the values which are available inside the centroids. So the k-means, the weights are decompressed using a lookup table during runtime inference, and k-means based weight quantization only saves storage cost of a neural network model. All the computation memory access are still floating point operations. So if this, we will consider the flow of the diagram, that we take the quantized weights along with the code book, we decode them and store the weights in the floating point representation, and then the inputs and the activations come in the floating point. We do convolution operation or whatever operation is required, and we add it with the bias again in floating point, and the ReLU operation, the activation is again in floating point to get the output. And this output we use to train the centroids again based on the things which we have discussed in the course in this lecture. So next is linear quantization. It's already 53 minutes, so there are almost odd 10-8 slides which are left in linear quantization, but I do not want to rush over to the topic. So what we can do is actually, because not to disturb the flow of lecture, you can pause the video, take a break up till this point. I'll cover the linear quantization in this video only, because else it will break the flow of topics which we have decided originally. So feel free to pause the video, take a break, and now let's start discussing the linear quantization. So it's almost I think around 10 slides which you have in linear quantization. This is what we are actually going to use in FPGA, so therefore I want you to be really attentive when we are discussing this. K-means quantization is something which is used in research and everywhere, but linear quantization is something which we practically use. So linear quantization is an affine mapping of integers to real numbers, and simply put, if this is the original weight matrix which we have, we represent this whole weight matrix by unsigned integer number. Since we discussed last time 2-bit unsigned int, signed int, again we are just going to take 2-bit signed integer number, and we subtract it with a 0-point number which is again in 2-bit signed int format, and we multiply it with the scaling factor. The scaling factor is in 32-bit floating point number. Once we do this operation, how we calculate these parameters is something which we're going to learn in the next slide, but based on this 2-bit signed int, if you choose, so how many representations you have which you can fill it inside this weight matrix. So if there is 2 bit, then equally spaced you can go from 2 raised to the power, again as we discussed in sign bit representation, the range is minus 2 raised to the power n minus 1 to 2 raised to the power n minus 1. So this is the range which you can go, right? So if it is 4, then you can go from 1 0 minus 1 minus 2, and if you are having 3 bits, then you can go from uh, just uh, just put 3 inside this, so 2 to the power 3, so it will be 4, and here it will be here also it's actually minus 1. So you can go from minus 4 to 3. So that's how you can, like, find out the linear space, and these are equally spaced. So depending on how many bits you are given, you have to calculate based on that. You do this operation and you obtain these numbers, the reconstructed weights, and then these reconstructed weights, you find out the error, what is the quantization error, and this turns out to be very small. So this is much smaller than what you have done in the previous k-means thing by representing it in a code book. Again, we have not discussed how to represent that code book, but we just eyed out and, like, okay, we have not gone through the method that how that code book numbers are effectively found. We've just, like, taken an example and eyed out, but given an example in your exam also, even in your exam portion, so you should know how to calculate it, further process from it, like calculate the reconstructed weights, calculate the quantization error. So linear quantization is an affine mapping of integers to real numbers, and here the idea is simple, that any real number r, it can be represented by a scaling factor which is in 32 bit into quantization, which is the quantized value minus the 0 point. So this is floating point, this is floating point, and both of these are integers. So the quantization, the parameters are quantized. So if these parameters are, let's say, 16 million, then 16 million of such things are, like, reduced in number, as opposed to just floating point, which remains the same, just a single value, which is floating point. So allow real number r equal to 0 be exactly represented by quantized integer z. So this is, like, the diagram which makes things very clear what is actually happening. So in this floating point we have an rmin and rmax, and there is a 0 in here in the floating point range, and then based on the number of bits we have, like if we have 2 bits, then we can go from minus 2 to 1. If we have 3 bits, we can go from minus 4 to 3. If we have 4 bits, we can go from minus 8 to 7. If we have n bits, we can go from minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. I had made a mistake here actually in the previous, so you can just correct that. Qmin, Qmax, this is how we do the mapping, that whatever the values are, they are somehow or the other mapped to one of these quantized values here in the linear quantization. Linearly, because these are spaces are all linearly spaced. So we can form two equations. Qmax minus z into s is r max. This is the first equation, that if this is getting mapped to this point, then Qmax minus z into scaling factor will give you r max, and Qmin minus z into scaling factor will give you r min. So if we subtract these two, then you can quickly get what the scaling factor would be, r max minus r min upon Qmax minus Qmin. Qmax and Qmin you already know, because this is your design choice, that what bit quantization you want. So it's there in this last slide as well. Qmax and Qmin depends on your choice of bit width which you have chosen. And rmax and rmin you can simply get by observing the weight matrix. So 2.12 minus 1.08 you can see here. So if you just put it into this formula, and you will get the scaling factor here. And how about calculating the 0 point? So you know rmin, you know Qmin, and at this point you know scaling factor. So you can just round it out to the closest value possible, and that will be your calculation of z. So in this particular example, rmin is minus 1.08, your scaling factor we had calculated as 1.07, and your Qmin is minus 2. So you round it down and you get it around minus 1. So this is your 0 point. And that's how we actually reached in the first slide, if you remember. This is how we actually reached to this point. Okay. Main aim is to actually minimize the quantization error, that this is what is minimized. So the summary is that given the weight matrix, now we know how to calculate the integer representation of the matrix. So we've just learned to represent the matrix in integer format, but now we have to actually look into the mathematics, that because ultimately what this whole integer like if it was originally in floating point, then this weight matrix was in floating point, this x activations which are coming, that was in floating point, and the output y. This is like a fully connected layer without a bias, right? With bias it would be plus b here. As of now we are just ignoring it. So we learn how to actually do, given the floating point operations, like given the floating point numbers and everything, we try to represent that whole thing in integer representation, and we try to do that mathematics. So how we can efficiently do that is what we're going to discuss in the next few slides. And we'll first of all discuss just the generic case of y equal to weight into input, then we'll add a bias, and then we'll understand how the convolution layer works. So consider the following equation, y equal to w into x, which you have to do, and all of these are in floating points right now. Obviously all means w and x primarily are in floating point, and multiplying that you will also get y in floating point. So we want to do the effective integer representation of everything. We want to calculate the integer representation of y also, because that's what we want to store, or that's what we want to do the operations further. So simply each of these floating point things can be represented by the affine mapping, as we had seen that real number is sq minus z. So here if it is y, then we are representing the subscript with y, and if it is weight, we are representing the subscript w, and if it's the input, it's represented with x. Our main goal is to find q of y. So in this equation, from this equation, we just calculate the q of y. So here is this simple term here plus z of y, which comes here, and the q of y is finally represented in this format if we multiply these two matrices together. Okay, but now from this matrix we have to identify certain things. So what is actually happening is this n-bit integer multiplication. You had seen that s, the scaling factor, this scaling factor were represented still in floating point, but these two were represented in the integer, in the integer bit. So let's say that in the previous example we had seen it to be 2-bit int, but let's generalize it into an n-bit operation, n-bit int operation, okay, just to generalize things. So obviously this n-bit is going to be less than 32 for most of our practical purposes, but we do an n-bit integer multiplication for all these things which you see here. This is also n-bit, 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 right? So all of this are n-bit integer multiplication, and we do the accumulation of all these, we try to, whenever we do the multiplication of these n-bit integers, we try to store the result in 32-bit integer. Why? Because we do not want it to overflow. So for the purposes of accumulating, we are doing it in a 32-bit register, but all the calculations in itself are n-bit integers. Out of this, and finally we add again n-bit integer addition. This scaling factor is something which we are going to discuss, because all of this is floating point. We'll discuss this, how to represent this effectively. But for now, first of all, understand that we are saving a lot of computation. Instead of doing 32-bit int mult, we're actually just doing an n-bit integer multiplication, and you had seen in the original diagram that let me just show that to you at this point of time. This is the thing which I am referring to, right? That instead of doing 32-bit multiplication, we're saving on energy, we're saving on calculations, we're saving on mathematics, everything, saving on memory as well. If we just reduce the bits, right? So all these operations, point is that we're just saving a lot of energy, we're saving a lot of computation when we are representing it in this format for calculating y as opposed to doing the floating point operations. And then we have an n-bit integer addition. What about the scaling factor? So the scaling factor, empirically, if you notice, this SW upon SX divided by SY, this is always in the interval between 0 to 1. This is a scaling factor which we have. So here, like the scaling factor, not in the terms of the individual scaling factors, but as a combined thing. So SY is always going to be greater than SW and SX multiplied. So what we can do is, any number between 0 to 1, it can be represented effectively by a fixed point multiplication, which you can see here, into a bit shift operation. So we can do the floating point here as well, but just to save on the operation, like the cost, we are actually doing it as a bit shift operation on a fixed point multiplication number. And this fixed point multiplication number is lying between 0.5 to 1. It's a fixed point, not even a floating point. So that's how we can save in this. And this factor which you see right here, ZX, QW, ZW, ZX, all this can be pre-computed because you already know about your weights. Like if you're in a certain inferencing process, you know about the weight completely. So you know your QW, you know your ZW. What you're not aware of is the QX, because that is coming from the input. So depending on the input, your QX will vary. But that particular factor, the 0 point of that X, that will remain the same. So QX depends on the input, but the scaling factor of the input and the ZX, that is already calculated, that is already pre-inferred. So that can be pre-computed. So this part can be pre-computed and only this operation needs to be done. In fact, out of this operation also, this QW into QX is the only heavy thing which you have to do. The 0 point into QX is anyways what you've calculated. So actually, like I'll be correcting myself a little bit. Both of these operations will take n-bit integer multiplication. So both of them are equally complex. Sorry, like I'll just correct myself. Both of these are complex. Both of these are n-bit multiplications. But based on an efficient mapping, we can choose ZW to be 0. The 0 point of weight to be 0. What it actually means is that we are choosing a symmetric linear quantization. So whenever we go for a symmetric linear quantization, our Z becomes 0. So ZW we can fix it to be 0, and that is when the equation would reduce down just to this thing here, and only one heavy lifting term would be there, which is quantized weight into quantized activation. The rest everything, this is n-bit integer. This weight seen can be rescaled to an n-bit integer by doing the fixed point and doing the bit shifts. This can be rescaled, and this is already pre-computed, so you don't have to do, it's like a pre-computed value, you don't have to calculate this every time. So only thing which you are left with is this n-bit integer multiplication, which you are accumulating in a 32-bit integer operation. I know some of this might be a little complex, so feel free to go pause the video or go over through this video once again in order to understand it, but things will become clear to you as you try to understand it intuitively and then through mathematics. Don't just depend on the mathematics, try to understand it intuitively why we are doing all this. The main goal again is to actually find out this QY in the most effective, computationally effective manner. Previously this instead of QY you were finding this Y, but we were spending a lot of computational power in calculating this Y. We were doing 32-bit floating point numbers into 32-bit floating point numbers, which is a very time consuming operation, alright, and very energy consuming operation as well. So we want to do it in a more effective manner, in an integer format, in a quantized format. Remember the slide which I showed you previously also, the energies which we are saving from going from 32-bit floating point multiplication to an 8-bit integer multiplication. Alright, just remember that, and that's what this whole effort of the mathematics is, to explain how we're actually reducing that. So here again, let's go through the fully connected layer, this time with the bias. So you can write down this whole equation in this format. I'll quickly go over through this. Feel free to actually work it out yourself. Here we have effectively chosen ZW equal to 0 as in the last using the symmetric linear quantization. So this equation reduces, this whole term reduces down to Z SW into SX into QW QX minus ZX into QW. Out of this term can be pre-computed because it depends on the 0 point of the inputs which is coming and the quantized weights which you already are pre-aware of. So during the entire calculation, this can be pre-computed. With each pass, this QW will change because you are retraining the weights, but here we are talking just about inferencing as of now, okay. So in inferencing, this will remain fixed. Then the zero bias of this also we can actually choose to be 0 for symmetric, because bias is completely in our hands. Bias is something which we can, like, fix it, and because it's just a constant term, so that's why bias we can actually increase it or decrease it based on our and we can later on compensate for this bias term. So ZB we can choose to be 0 and SB we can choose it to be SW into SX. We can take out this, then the whole thing SW into SX outside, and what we're effectively left with is this value inside here. Same thing operation here, this QB into ZX QW, we can pre-compute this whole thing and we can call it just as the Q bias. So this thing here right now is a Q bias and it's just a constant, which an n bit constant. This ZY which we'll actually learn how to we'll discuss it in maybe somewhere in the next lecture, that how we calculate this ZY. Or we can skip this information as of now, like it's not that important, but just for the completeness sake, we'll discuss at some point of time how to calculate ZY. Main thing is this QY which we have obtained using this formula. So this thing effectively can be rescaled to an n-bit operation. This operation right here in the bracket is nothing but n-bit integer multiplication, and which we're storing in a 32-bit integer addition registers, accumulating into a 32-bit integer add. And both this QB and QBias are 32 bits, and this is n-bit integer, which is a simple addition operation. So that's how we calculate QY. When it comes to doing the quantization of the convolution layer, the same things will follow. That if originally we were doing in floating point y is equal to convolution w comma x plus bias, then by choosing symmetric quantization and all these things here, the q bias would now be just qb minus convolution of qw into zx. And again, it's a constant thing, so you don't have to worry about this pre-computed constant thing. It's just one-time computational cost, so we don't make it like a huge ruckus out of it. The main thing is that n-bit integer multiplications you will be doing inside this convolution operation. Obviously there will be more operations here, but each operation will be n-bit integer multiplication. And yes, that's linear quantization for convolution. And if you have to follow the flow of this, then we take the quantized inputs in integer format, we call it qx, and we have the quantized weights which in qw. Along with this information comes the information of zx and scale x, and also zw and scale of w. We do the convolution operation in int 32 only. We add the quantized bias because this q bias is a 32-bit number, so we add that in 32-bit. We have the scaling factor again coming as an in-bit integer, so we expand it to 32-bit and then we add it, we multiply it with this, so it's a 32-bit int into 32-bit int. Finally, whatever integer we get, we do an addition operation of that, so it's an addition operation in integer, and we finally get the quantized outputs qw. Sorry, here it's quantized outputs qy. It's qy. So you see that if we do the int8 linear quantization, then for floating point accuracy we had 76.4, but for 8-bit integer quantized we have accuracy of 74.9 or 75.4. And the latency versus accuracy trade-off you can see in this chart, that for floating point operations, for the same accuracy the latency is more because the number of operations which has to do is more, right? So that is the thing which we have tried to save on, because there are less number of computations and you do that more quickly. So here in linear quantization we had storage of weights in integer format. Also the arithmetic which we did, which in the last 4-5 slides you had seen, that arithmetic also, the computation also was an integer only, as opposed to k-means in which you had to ultimately come back to the floating point arithmetic in order to do your calculations. So this is the summary of today's lecture. We discussed about the basic data types, we discussed about the neural network quantization basics, and we looked into k-means and linear quantization and how the integer mathematics works. In the next lecture, we'll talk about pruning. Thank you so much.